I wanted to talk about something that was a recent insight that I gained that I thought was useful, something practical, which actually involves this thing, assert. So I was around a long time ago when Java 4 came out, and Java 4 had something in it called assert. It was a new keyword. So the idea is you could sprinkle assert in your code and make it better somehow, right? So I wasn't sure what to do with that. I mean, I wasn't sure when to put asserts in my code. That was like, I just didn't know. I understood how it worked, but I didn't know how to apply it, right? So in those days, I was doing a lot of interviews of people who design languages and people who write books about programming. And Dave Thomas and Andy Hunt had just come out with The Pragmatic Programmer. Has anybody heard of that book? Is that okay? So some of you know that one. It's a good book. And they had just come out, and so I decided to interview them. And one of the things that they did talk about assertions in their book. So I said, well, I'll ask these guys, you know, how should I use assertions? And what I said was that the only one time that I felt like I felt an urge to use one is if I don't fully 100% understand my code. So what I wrote, this is in an interview I published, I wrote, when I'm not 100% confident I fully grasp the complexity, that's when I feel the urge to put in an assertion. So, you know, usually I try to understand what, you know, write code that I'm sure is going to work, but sometimes it gets too complicated. I'm like, I think it's supposed to be, you know, my intent is that this is true at this point in the code, but I'm actually not sure of it, so I stick it there, right? So what he kind of said in a nice way, a diplomatic way, was that's absolutely wrong. I shouldn't do that, right? So what he said is whenever I find, well, this is Dave, whenever I find myself putting in asserts because I don't really understand what my code is doing, I try to use that as a warning bell that I should actually step back and simplify the code so I can understand it, right? So that was his advice, is that if you're putting asserts in your code because you're not 100% sure or confident it's going to work, then that's actually a different problem you got to solve, right? Is go back and make sure you understand your code and it works. And then he says, and then put decent asserts in, which is actually what my question is like, what are decent asserts? And he never actually told me, so he kind of dodged the question. But that's basically, I didn't get an answer back then, and so I didn't still know exactly how to use them, so I just ended up using them in one place. So where that came from is another guy named Bertrand Meyer, who designed a programming language called Eiffel. Has anybody heard of Eiffel? Well, a lot of people heard of Eiffel. Okay. Oh, well, it's designed by a French guy, so maybe there's some connection to Canada. But anyway, this guy designed it around the time of that C++ came out, and it was kind of competing with C++ and lost for mainstream, sort of like the next mainstream language, to C++, which really was frustrating to Bertrand. He actually came to a company I was working at and gave a OO seminar, because we were trying to move from C to C++, and he was giving C++ workshops and seminars because that's how he could make money. But his workshop was really, he would show Eiffel and talk about the concepts, and then and in C++ it looks like this, you know. So he was kind of like, kept going back to Eiffel. It was kind of like an Eiffel infomercial to an extent. But actually, that's where I first learned my first things about OO was from that Bertrand Meyer, right? But one of the things that was different in Eiffel that wasn't in a lot of other languages was he had this thing he called design by contract, trademark, where you actually, when you write a function, you have to specify that function with assertion. So he really fleshed out the idea of what an assertion is, and what, that it throws an exception and what that all means. And he had a very full-blown feature set for assertions in Eiffel. So this is This is a example of Eiffel code of like a function that does the square root. You can't just say what the algorithm is for computing the square root. You have to have three things. You have to have a require clause, which is a specification or a statement of what the preconditions of this function is, which is when someone calls it, what has to be fulfilled, what promise has to be fulfilled by the caller. That's a precondition. So for square root, it takes a real, which is like double, and that can be negative, but you can't actually you can't compute a square root on negative numbers. So his precondition is that, you know, the double passed in has got to be positive or 0. And then do is actually where you do the thing. That's actually the body of the function. And then the third clause is called ensure in Eiffel. And there you have to make another assertion, which is a statement about the state of the world after the function executes. And in those days, people were thinking most functions have side effects. So you would look at if the side effect did its thing, or if it had a result, you would look at the result. And he had like that capital R result there just means the result. I mean, this is sort of some of the syntax he had just to support this concept of assertions and specifying in the code. So what he did here is he said, well, the postcondition is if you square the result, so the result's supposed to be the square root, right? So if somebody passes in 4, the result should be 2, right? So you square that, you get 4 again. And if you subtract the original 4, you should get 0. So in the ideal world, you will get the same, you'll get 0 at that point. But because it's floating point arithmetic, it might be slightly different. And because it could be positive or negative, he computed the absolute value. So now it's a tiny little positive number, and you can say make sure that's less than or equal to tolerance, right? So what that shows is 2 ways to use assertions in production code, right? So what actually happened in the marketplace is that this didn't really win out, and I think a way to see that is that you can actually do this in Scala, this kind of design by contract thing. How many people have heard of assume in Scala pre-dev? Not a single hand. Well, there's 2 hands up, but he was just stretching and it made him put his hand. There's one person heard of it, okay. 2. Yeah, so it's not many people know that it even exists. So let me just give you a quick demo of it. It's just like assert. So I'm going to make an x equals 1. And if I say assert x is greater than 0, that's going to return the unit value. If I say assume x greater than 0, this is just from predef, it does the same thing. If I say x is less than 0, if you say assert, gives you an assertion error that says assertion failed. And if I say assume, it says assumption failed, but it's assertion error. It does the same thing, essentially. So it's like, that's there. That's been there the entire time, and you just didn't know about it. Think how much more productive you'll be now. And they both also allow you to like put a clue string in here, because when an assertion fails, it goes into the log, and you want to like find out some information about it. So you could say $x or x was $x, let's say, and now you get a little bit more information in the error message, and the same thing with assume, right? So they work exactly the same way. The only difference is assume was intended for precondition checks in particular. That's all it was. So you can say, well, when I'm implementing the body of this method, I assume this is true. And that means it's the responsibility of the caller. So that's a precondition assertion declaration, right? And then ensuring was something that that came into being when we were writing the chapter of the book about how to use design by contract in Scala, because it didn't exist. So, it kind of has the word ensure in there, like Eiffel. But the way it works is it's just, again, something in predef. It's added to any type by an implicit conversion. So like here I'm calling it on math.square to x, which is the candidate result of the function that I want to pass back to the caller. But before I do that, I actually invoke ensuring, and that guy takes a function that will be passed, ensuring will pass the candidate result into the function, and then you do an assertion on the candidate result, right? So let me just show you an example of that guy. So if I say 42, let's say that's my candidate result, I'll say ensuring, and now here I have a function that's going to take the candidate result and say, well, it has to be greater than 0. Well, let's make it fail. Let's say it's supposed to be negative. I get an assertion error. So it is an assertion, right? But if it succeeds, it's a little different than the other assume and assert, because it doesn't return a unit like assume and assert. It actually returns what ensuring was called on, because you need to actually return that back to the caller. So that's how it gets back to the caller. If you look back at this guy, after ensuring is done, after ensuring invocation is done, if the assertion succeeded, you get whatever math.square root of x computed returned back, and that goes back to the caller, right? That's how ensuring works. So it's just like Eiffel. I'm going to back up one slide. It's just like this. You have a require clause at the end, which we call assume, and you have an ensure at the end. So this is what, I actually liked this concept. I thought it was formal. I kind of like the fact that you formally say, well, when I write the method, I have to think about how to specify it. And this is like putting test assertions in the code next to the code, which they're nearby, which is kind of nice. And it's also very formal because he said this is a specification of the correctness. That's how you specify the correctness of the function. And you sort of test it. His idea was that you would mostly have these things enabled during development and test, but disable them during production. So that was maybe where that idea of assertions are things you can elide at runtime came from. I'm not sure if it came before that, but that was definitely in Eiffel. There was just all kinds of ways to take assertions out and just like turn them on in one class and that kind of thing. So anyway, this lost in the marketplace of ideas, this lost in the marketplace of ideas to this. So this is what we do in Java and what we do in Scala. Where require came from is when we were writing that same chapter in the book, I didn't like that assume through assertion error because this is on the JVM and I was an old Java guy. Now I'm an even older Scala guy. And it was unidiomatic to throw assertion error. And especially that make it possible for someone to elide that. Like assume you can elide. What happened on the JVM is you check preconditions and you throw some more specific exception like illegal argument exception or illegal state exception or null pointer exception if somebody passes something null where they're not supposed to. That was the culture in the JVM. So we added this thing called require to predef, which, I mean, how many people know about require? Okay, so that's a lot more people because that's actually what we use the most. So if I say require x is greater than 0, which succeeds, again, returns unit. If it's less than, it's the same as assert or assume, but it says illegal argument exception. So anyway, that's really the same thing as, it's like a precondition check you can't turn off. And that was actually the default in Eiffel. The default in Eiffel was if you didn't do anything special and you ran an Eiffel program, precondition checks would be turned on, the require clauses would execute, but the post conditions would not. So that's sort of what we did. And then the other thing that happened is like if you look at math.square root of x, that's what we do. Sort of, we don't even check the post condition. It's sort of like I can return anything I want, right? And that's one in the marketplace because what we decided to do was take that assertion, the post condition one, stick it way over somewhere else in something called the tests. And that's where we do our post condition checks. So we have this other thing called a test where we will, for some set of examples, look at the post condition, call the function, and look at the result. Right? Look at the state of the world after it. So this is what one in the marketplace of ideas, I think, is unit testing. And precondition checks you can't turn off. Okay, so what I did here, though, is I didn't just check a few examples. I use a for all because I think to get the kind of formalism which I liked about Eiffel, I'm going to back up 2 slides again. This is the Scala version. What this assume ensuring says is that no matter what x is passed, if the assume clause succeeds, then the ensuring clause must succeed. So that's sort of for all x's that can be passed in. This says that implicitly, but in a test, you actually have to say for all, right? And it's not going to test every double because that's too large a space, but it is saying that, right? So that kind of does the same kind of specification. And what we have to do in that case is repeat the precondition check in that whenever clause. It says whenever x is greater than or equal to 0 and not positive infinity. That's the precondition check. So I've said require over here, and I said whenever over here. So I had to say it twice. But then I just put the postcondition thing there. So anyway, that require is a kind of assertion in my production code that I do use all the time. So I think require is good to do if you if something can go wrong like that. It's better to actually check it and fail fast, so that because when that thing actually is false, it means that the program detected a bug in itself. And so if the program detects a bug in itself, it can't proceed, and you really want to get out of there fast so you don't do more damage than maybe has already been done, right? So I think that's a good thing, but I think it's an expression of hope. So this talk is hope, faith, and proof. The reason I think that's an expression of hope is because it's exactly what Dave Thomas told me I shouldn't do, right? The reason I put it here is because I'm not 100% sure someone's not ever going to pass a negative number in here. Because even if I've got 100% test coverage of my code and it all passes, and I'm pretty confident this is, my code is never going to pass a negative number here, what if someone changes it down the line a year from now and they don't notice that and it happens? It could happen. So that's why I always leave it in there. I put it there. So it's an expression of hope because there's no evidence that I can see that it's always going to work, essentially. Okay. So what I might want to do is, I think if you can, every time you do a require, it's good to do them if you need them. Don't leave them out if there is actually a requirement there. But when you write one, think to yourself, well, is it practical to put it in the type so that actually the precondition is fully represented in the type? And so we've been adding a bunch of any vowels to Scholastic that capture lots of things like posint and negint and that sort of thing for various primitive types. And they're any vowels, so at runtime the performance is usually, this should be the same. They don't box unless they would box as a primitive would box anyway, in theory. So we have one called POSZ finite double, which is a bit of a mouthful, but what that means is this is a double that is positive or 0 and finite, so it's not infinity. So there's a way to say infinity in double, and it's also not a number. So that's like it's constrained, and that's actually what we need for square root. So if I change the parameter type to that, I don't need to have the require anymore. So I think that's a good thing because now there's one less place where my program could blow up if someone passes something bad, kaboom, right? Okay. So what I have in my comment there is that POSZ finite double is an expression of faith because I just believe that it's going to work. I mean, what if there's a bug in POSZ finite double? It actually may not. It could be negative, right, if there's a bug in there. But if I didn't believe in the type, then I would put requires everywhere anyway, right? Like if somebody passes an int, I might say require is actually an int. And that would, you have to like trust something, right? But the reason I say I'm not sure, the fact that there's a type there doesn't prove it is because there could be bugs. So has anybody heard of Curry-Howard isomorphism? All right, so this is, there's interest in proving programs correct, and because it's so hard to get code right, they want to be able to say, well, this code, because we proved it, then we know that's correct. That's a valuable thing to try to do. And there's this isomorphism, there's this similarity that was noticed between logic, where you can actually make assertions about like statements about things, propositions, and type theory. So logic and type theory. Types you can see as logical propositions, and in programs as proofs, right? So what I think is that the trouble I have with this is the reason I don't think of like this type as proving that it's positive, 0, or finite and a double is because there could be a bug. So I have faith that I'm just going to believe it, but I don't actually know. And so one of the things, for example, you might expect a double to do is when you divide two doubles, you get the proper double answer back, right? But there actually could be a bug in the compiler or in the JVM or in the operating system or maybe in the Pentium chip that you're running on, because there was a version of the Intel chip that had a bug in the chip that lightning kind of had to strike. You had to divide the exactly correctly two numbers, and there was it sounded like a lot of them, but it was pretty hard to actually hit, where it gave you the wrong answer back. And then another thing I can tell you more, I never got that because that's hard to get, but it's possible, right? So even double, I'm not sure you can trust. But I have faith in double. But I was, we ported Scala test to Scala.js, and that runs on JavaScript. And Chi Seng, the guy that helps with Scala test, he he checked in a pull request where we're testing pos int. And the way we test it is we compare it with int to make sure it's doing the same thing. So it's a really good use case for property-based testing where you say, I have a known thing that I want this to behave like. So I was doing that, and he had a case, he had to add a case, not a number, but it's an int. So we actually had to trick the compiler into letting us do that because that is a type error. But what happened was if you divided by 0 in JavaScript, it actually gave you not a number. If you divided an int, but any int by the int 0, you got double not a number. It actually changed its type at runtime. So I'm like, that sounds like a bug. So that was a bug in the Scala JS compiler. What was funny about it was I did tell Sebastian, the guy who was the main guy in doing Scala JS about that, and he goes, oh, sorry, that's a bug. The answer should be 0. I'm like, okay, that's probably better. But anyway, that's why I think these are expressions of faith. And what we do is not so much like mathematical proofs as science. I think that what we do is more like the scientific method, where Einstein has been quoted as saying this, and it's not clear he actually said it, but it's a good quote. So he said, no amount of experimentation can ever prove me right. A single experiment can prove me wrong, right? So that's sort of the idea of science, is that you come up with a theory and you don't just take it on faith. What you do is you say, well, I need to come up with an experiment that can disprove it, right? And you do that, and then you think of other experiments, and multiple people, try to repeat them, and that's sort of the process, right? So no matter how many of those actually succeed in sort of validating the theory, it doesn't prove the theory, because sometime later, 50 years later, 100 years later, somebody could come up with an experiment that, oops, it's actually, we need to modify our theory. It doesn't work anymore. But what happens along the way is that you can get scientific consensus, which means that there's so much evidence, like so many experiments have been tried, and that all kind of adds up, and it makes sense that this probably is true, and we believe it. So you kind of take it on faith. So there's that aspect, I think, of like what scientific consensus to me is faith in that a theory actually is correct. So where my insight came from is this last bit. What I wanted to do with this square root method is, I happen to believe that math.square root, and what this function does, by the way, is math.square root is perfectly usable, but if you pass a negative number in, you get not a number back. So what this guy does is he throws, not this one, the previous one through illegal argument exception. This guy they just won't compile, right? But that's what the difference is. But it's still returning double, and if you take the square root of a number, it's also going to be positive, 0, or finite, right? That's what I believe. So why don't I return that value? So I can, but the trouble is that I have to actually call a YOLO method. So I'm going to show you a real quick demo of how these things work. So I have to import any vals. I'll just take all of them, and I'll say posy finite double. And if I say 42.0, there's a macro that just makes sure at compile time that is valid. So that's why I got one back. If I say negative at compile time, it's going to give me an error, right? If I say val x equals 42.0, let's do 4.2, why not? And val y equals negative 4.2. Then I also get a compiler error because I can't prove that either of these guys, at compile time I can't prove they're valid. So what the compiler error tells you to do is use a different factory method called from that will give you an option back. And the reason in part is because I didn't want to just move the problem. In other words, x is at runtime determined to be valid, so I get a sum. Y is at runtime determined to be invalid, so I get a none, right? And I didn't want to just move the problem from, take away the require, because that's what we did here. We took away this require when we added the posy finite double, right? Here's the require, and then I took it out. So I don't want you to be able to get an exception when you create posy finite double, because I would just have moved the problem, right? So I was trying to be idealistic, and I didn't give you a method to make an exception. I gave you the from method that would give you an option back. So that's more, I thought, principled, right? But then I found myself, after using this for a while, I kept doing this. Like right here, I would do it. I would create an option and then call get. That's the you only live once, it may blow up method. Because I'm pretty sure it will always work. That's why I would call that, right? So I realized that this is kind of stupid. Even in the macro that when you just say posy-int or posy-finite double in 42.0, that thing rewrites that code to call from.get. So you create an object on the heap and then throw it away right away, which is just stupid, right? So I realized that I'm going to have to give you a method like that. And I was trying to think of what to make it, to name it. And so the leading candidate was unsafe from, because it's kind of long-winded, which would discourage its use. And it has the word unsafe, and you don't want to see the word unsafe in your code, so that would also discourage its use. And it's truth in advertising, right? Because this really is unsafe. It could blow up if you pass in an invalid number. But then it hit me, and this was my insight, that it's kind of like ensuring. Remember ensuring, you call it on 3.0, and then there's a function that's an assertion. If it passes that assertion, you get 3.0 out the other side. So just the 3.0 goes through this assertion, or you get an exception, right? So here, when I'm saying posy finite double unsafe from, I'm passing in 3.0, and it does this validation assertion on it. And if it succeeds, out the other side comes 3.0 again, the same thing, but with a more restrictive type. So I realized that this is actually a new kind of, like a different kind of assertion that is like ensuring, but you get a more specific type back. So that's why I called it, I realized I should name it ensuring valid, which is an assertion in your production code. And so that's what it's called. So now there's this YOLO method in all these any-val types that will blow up if you pass it an invalid thing. So I did just move the problem, right? I've just moved it from require to when you create the thing. But what I think is different is that require is always an expression of hope, because I have no evidence that it's going to work. You know, I don't know what's going to be passed in, so I hope it's always positive, right? Ensuring valid can be an expression of faith if it has nearby evidence. So in this case, I had nearby evidence. Well, here is a valid literal. So here, if I just say x equals 2.0, and I then call ensuring valid x, well, x, I happen to remember it's 2.0, so that's my nearby evidence that it's always going to work. Right? So that's different than require, where I have no idea what x is going to be. And then down here in my square root method, if I say ensuring valid, I have faith that's going to work because I believe I understand what, how math.square root works. So, so that basically what I figured out after, I don't know how many years ago it was I talked to Dave Thomas, but I actually got an answer to my question. It's like, how would you use assertions in production code? Where would you put them? So I think there's two times you should use them. One is these requires, where you're doing precondition checks and you don't turn them off. And the other is assertions that give back the same value with a more specific type. Because now what you've done is you've moved that thing you're asserting into the type where people will believe it, right? So the two guidelines I have is basically when you see require, you should think about, can I actually get rid of it by moving that constraint into the type? So that's like get rid of most of the places where you have expressions of hope. So you want to squeeze all the hope out of your code. And then it's okay to have these ensuring valids as long as there's nearby evidence that sort of gives you high confidence, like scientific consensus, that it's going to work, always. So I think you may end up with more of these kinds of assertions than the require you remove, maybe, but I think it's still better, because if each one of these is nearby evidence, then I think most of the time you'll get that right? I think that's better. So anyway, that's my talk. Before I take questions, I just want to mention that at Artema we are doing consulting, and we are looking for people. So if anyone's interested, you can come talk to me or email careers. And I have some time for questions. Anybody have a question? Anybody? Yeah, you.
Yes. So.
Yeah, sure.
So this approach seems like it's a bit more reliable than just asserting or assuming, but it's still essentially a runtime check, right? So you still.
Correct.
Does Scala have something like a guard clauses where you can actually have a compile constraint on a method signature saying, or public signature saying, this is the range of data at value level, like this array only accepts up to like length 3 or non-empty integer, which there's sort of a question of fate, and like you know for sure because otherwise the code doesn't compile.
Yeah, so there's two ways you could do that. I think I don't have to repeat the question because it was so loud, right? Yeah. Or do you need to repeat it for the...
You want to repeat it for the camera.
Okay, I'll repeat it for the camera. Unfortunately, I forgot what it was by now, but no, the question is there something in Scala that can do things like say this array must have length 3 or that kind of add kind of constraints to type. So one thing you can do is make a new type, and types are pretty concise in Scala. There's so this anyvals package, I do have a base class you can extend to make types that have compile time checks like that. There's another library that is called refined, which is kind of you can make expressions and do things like this array. Well, I'm not sure you can do it with an array, but seek can have a length or a max length, things like that. So yeah, the type system is rich enough to just do that stuff fancy, but I think sometimes you can just make a new type and it's pretty concise, and then it's maybe easier for people to understand sometimes. Yes, anybody else? It's a very quiet in here.
Problem is
you know,
are way too comfortable.
You know what? I think because I was talking about faith, they sort of feel like they're in church and they don't want to. Yeah, but anyway. Okay, well, thank you very much. Oh, wait. Yes, I was.
I might have missed this, but so what could you do in the future to make it so that Scala will figure out better what to do, like if it doesn't know? Like if you pass in X into that type and then it doesn't, it throws an exception then. Is that the best you can do?
Well, I don't know. I mean, the future is you know, it's kind of cloudy. Is that me making that? Yeah, I don't know. There's research with dependent types. Like there's Idris and Agada, where they're really trying to put more and more into the type, like more assertions about values into the type. Scala doesn't. I don't think Martin wants to take Scala too far in that direction. But yes.
Just to follow up, years ago there was all that kind of type annotation stuff in Java, that there were going to be all kinds of wonderful static checking and stuff.
Yeah.
Did that go anywhere, or is that stuff going to be used in Scala in the future?
You can make a Scala compiler plugin that does extra checking outside the type system, but the type system is so powerful in Scala, you can also do a lot of stuff in the type system, but both of those things are possible. Yeah. Okay, anybody else? Yes?
Okay, so you talked about using the ensuring valid or just the apply function from what was it, double Z positive?
Mm-hmm. Yeah.
Yeah.
Mouthful.
So,
just call it mouthful.
So I think like you could basically every time you just get some data or some kind of information that comes at runtime, and then if you return an option, you could always then just, I don't know, flat map all of these options on top of each other, and then you get a full program that is completely void of exceptions in the language sense. But you would obviously, I guess, have exceptions in the sense that your options might be none or something. But what if you, I don't know, what if you turn that into an either instead, and actually documented like the actual error? So I feel like that might be a nicer experience for like the user, I guess, the programmer. Oh God, feedback. Sorry. Okay.
Okay.
So yeah. So have you thought about that, or are you kind of content with the exceptions approach?
No. I think exceptions in Scala, the idiomatic way to use them is when the program can't recover So an example is the program has detected a bug in itself. If your program can recover, it's better to use an option or an either, or an either. Either an either or an either. Or a try if you're going across threads. And then the program, then it's in the type that this could happen. But if it's really, in the case where the program can't really do anything with the error because there's a programming error, then there's no point to do that. You just throw the exception, that's what that's for. And then it goes, maybe it doesn't abort the whole code program, but it aborts that activity, and maybe it's caught on top and it's logged for a human. So yeah, that's how I split those. I don't know what time it is, so you can cut me off if there's a...
Yep, we still have time.
Okay. Anybody else? Yes?
So you said it's usually better to move a runtime required check into a compile time type check, which I totally agree. Is there ever a good, I mean, can you actually make a rule about when it is good to use a require? I mean, is this
Yeah. Well, I guess that the guideline of this talk is as little as possible use a require, but only if you put that in the type. So that and sometimes it's just not practical. It's too much trouble to put into the type. And then if you're gonna if it really is there, you should put the word require so that it fails fast, and you get a nice forensic data into the log file. Yeah. Yes.
So what do you do if the require is very expensive computationally?
Wow, that's a good question. Well, that was the idea of...
For example, when I do a graph and I want to check if the vertices I'm referencing in the edges are actually in the vertex set, for example. That would be quite difficult to express as a type, but it's also a bit more expensive than just checking against 0 or something like that.
Wow, that's interesting. That's a great question. The question, to repeat the question, it's essentially one of the ideas of Eiffel, that you can turn off these assertions is because they were seen as very expensive, and that was when CPUs were a lot slower, memory was a lot smaller and stuff. But still, they can be expensive today, and it requires these precondition checks. Usually, we never turn them off. So, what if they're expensive? That's a really good question. I'm not quite sure the answer, which is why I think I like it. But you said it's hard to put in the type, but I would. I mean, if you really believe for some reason that it's true, it'd be nice to assert that and move it to the type somehow. And you do it once, and you can use it later. But if it's being transformed all the time, you have to do it over and over. I don't know. Actually, that's a performance question, maybe. You're trading off performance and failing fast, which maybe you don't have to fail fast. It's just usually a good idea because you want to stop before damage is done, like corrupting a database that's harder to repair, right? But maybe that's not your situation. So nothing is sacred in this talk about faith. Okay, all right, well, thank you very much.